let's get started. So again, hi, thanks for the opportunity to talk about Palette. Uh, uh, Over the years, Palette has supported feature engineering needs across all major use cases at Uber. As adoption has rose, several scalability challenges have emerged. And we're going to present today the advances in the feature store that have allowed us to deal with these challenges. Thank you for the introduction. I have been involved with the feature store for the last 3 years. I have been responsible for the overall architecture of the feature store and also feature engineering infrastructure within Michelangelo. I also directly manage a team working on the feature engineering infrastructure in Michelangelo. Co-presenting is Nicholas Marcotte, who has been with the team for over 2 years. He has led feature store scalability efforts across the board. He has also contributed extensively to all components of Palette. So just overview, you're all familiar with all this architecture. This is what the feature store has come to become. And at its heart, it is a dual sort of database system. It has an offline store that persists historical snapshot of features for use in training and offline predictions. And it has an online store that persists the latest snapshot of features for use in real-time predictions. The Palette feature store does have a self-service authoring system to create your ETL pipelines, feature generation pipelines. There is a monitoring system that tracks the quality of the ETL pipelines as well as the quality of underlying data produced. We also support a feature discovery system to search for features relevant to your machine model. And finally, on the right bottom here, we are deeply integrated with Michelangelo training and serving stack via the so-called transformer framework, which is able to assemble or join features and transform them in a way that is semantically consistent across training and serving. Oops. Just give me a minute. A little bit of a technical glitch here. I just lost the screen here. Sorry about that. All right. Yeah. All right. So a brief history of the feature store. I already mentioned, like back in 2016, we started talking about it, created a buzz. 2017, the blog announced about Michelangelo. We onboarded a few use cases back then, popularized the concept both inside and outside of Uber, and rest, as you know, is history. In the second phase of our development, we have been focusing a lot on scalability. We scaled massively to onboard some of the top use cases across Uber, as well as build functionality such as near real-time features to sort of onboard some of the top business critical use cases. In the most recent phase of our evolution, we have focused a lot on the ecosystem surrounding the feature store, specifically building infrastructure to integrate better with the adjacent data platform, as well as Michelangelo, to accelerate the pace of model development. So what exactly are the problems at scale? I'm going to start with online serving. Palette today serves tens of millions of feature requests per second, a lot of them originating from the explosive growth of our delivery business during the pandemic. And not only do we serve at this scale, but we ensure that the P99 latency for most of our use cases are in single-digit milliseconds. Second, not only do we see models using larger feature datasets, but also training over larger periods of time. In some cases, this can result in the use of hundreds of terabytes of feature store data that needs to get joined against the target labels. Third, as adoption across the company has increased, it has meant thousands of pipelines that need to be maintained. So how do we ensure that these pipelines are healthy and producing high quality data? And last, given the tens or hundreds of thousands of features in the feature store, how do we select relevant features without having to build the same features all over again? So with that, I'm going to hand it over to Nicholas, who's going to dive a little bit deeper into the online and offline serving. All yours, Nicholas.
All right. Yeah, hello everyone. Now I'm going to help us take a little deeper look into each of these scalability issues that Amit summarized and discuss how we can have addressed them. First off, let's tackle online serving scalability. Now, for more than over a year, the pandemic has had a large impact on Uber's business. With more users stuck at home, Uber has seen large growth in the number of customers ordering from Uber Eats. For an app like Uber Eats, where we need to surface the most relevant items for a user, email recommendation systems play a huge role. A typical recommendation flow starts with the user opening the app. At that point, we need to fetch features for thousands of candidate restaurants. And for each restaurant, there are often multiple models, each which depend on many feature groups. This feature request fan out causes a huge reload on the feature store. Next slide. To address this fan out and improve both latency and scalability, we've performed 4 major optimizations, which are choice of serving infra technologies, table consolidation, custom partitioning, and efficient batch data writes to the online feature store, which we refer to as dispersals. Next slide. 2 years ago, when I first joined Uber, we used Cassandra to serve all features. As hardware costs grew, we saw a large opportunity to use the technologies best suited for specific use cases. This slide depicts cheap and fast solutions on the left and more expensive solutions on the right. As a fully featured NoSQL database, Cassandra still serves as the backbone for most features. It is still especially fit for features modeled at the user level, where we have hundreds of millions of entities and terabytes of data daily. The first new technology we decided to add was a local in-memory cache. It is perfect for small data sets that can easily fit in memory and have high hit rates. It is cheap, fast, and alleviates issues stemming from skewed partitions. For larger feature sets, we attempted a sharded local cache solution, but did not end up pursuing it due to operational overheads. So instead, we've gone with Redis. It has proven to be far more cost-effective than Cassandra, and today handles Uber Eats feature sets such as restaurant data. Next slide. So now on to table consolidation. One of the core ideas in any feature store is the idea of feature groups. When users onboard new feature groups, they typically organize them based on several factors, such as feature ownership, what job produces the features, and how they are semantically related. When a new model use case onboards, they may find that features they need exist across several different feature groups. In the restaurant recommendation use case, a model may find these 3 example feature groups all related to restaurants: a ratings related group, one for wait times, and another for embeddings. Next slide. If we use a simple approach of creating an online table for each feature group, we end up with an extremely high query fanout when fetching features. In this case, a model requesting a single restaurant's features will end up issuing 3 separate queries, since the data lives across 3 separate partitions, one for each table. Not only does this fanout create extra load on the underlying database, it also creates high tail latency issues. Next slide. So the solution for this problem is fairly straightforward. If we organize the data into a single consolidated table that matches a use case's query pattern, then the same data can be fetched by a single database query. This can drastically reduce database load and latencies. Next slide. As data scientists try to squeeze out more performance from their recommendation models, they will likely add very personalized features into the mix. As an example, relevant to restaurant recommendation, this table represents user-specific ratings per restaurant, where the primary key is composite, made up of a user ID and a restaurant ID. In the standard key value feature store approach, the entire primary key is used for partitioning the data online. In this case, both user and restaurant. Next slide. If we go with this partitioning scheme, then even for the same user, each of their restaurant ratings lives on a different node. When we want to evaluate a set of restaurants for a given user, we would need to issue a database query for every single restaurant to get the relevant features. This results in a similar fanout problem as described before. And again, we see wastefully high QPS and tail latencies. Next. To address this, in Palette, we allow users to customize the online partitioning schema as part of a feature group's configuration. To optimize for this use case, user ID is set as the partitioning key, depicted here in green, whereas restaurant ID is configured as the shard local key, colored orange. This ensures that a single query for these features translates to a single database query, landing on only one database node. Within that single node, it is able to use local indexing to then find the relevant restaurant ratings. With the power of custom partitioning, there also comes some responsibility. When deciding on the partitioning scheme, feature store customers should avoid very large, skewed, or hot partitions. Next. The last two solutions focused on reducing query fanout and high-tail latency while serving features online. Now let's take a look at how writing batch data to the online feature store impacts scalability. Despite optimizing dispersal pipelines to write data in Cassandra's internal SS table format, we discovered a problem with data fragmentation and excessive compaction. As shown on the slide, essentially every Spark task streamed to every Cassandra node, creating lots of small files. This meant two things. One, read requests were slow. For a single request, Cassandra had to look across many SS tables for the relevant data. And two, Cassandra nodes were overloaded. They were too busy compacting all the small SS tables into larger ones. Next. To resolve this issue of data fragmentation, we replicated Cassandra's data partitioning and replication logic in Spark. By aligning these two, each Spark task now only streams very large chunks of data to a single Cassandra node, reducing the need for compaction. With this, we saw drastically improved read latency and Cassandra server load. In addition to dispersal optimizations, we also have experimented with and fine-tuned other Cassandra client and table configurations to optimize for performance. These include compaction algorithms such as leveled compaction strategy, read repairs, speculative retries, and so on. Even some lower host level SSD configurations made striking improvements in disk read performance and overall latency. Next. That concludes some of the major optimizations we've made to the online feature store. Now let's jump into offline serving. Here we have some of the main challenges we face. How do we tune Spark to handle joining huge tables? When performing point-in-time joins looking back at historical data, this can be difficult to manage. How can we avoid OOMs and skewed joins? Variation in dataset size, cardinality, and skew all produce unique challenges here. And finally, how do we speed up joins? When training a model, users want to focus on quick iterations to find the best performing model. They don't want to always be waiting for large joins to complete. So how can we speed up this process? Next. One of the first things done in order to easily manage joins was to break them up into manageable batches. For instance, instead of attempting a join on full 3 months of data, we could break it into smaller 1-month chunks. With this solution, as long as the join for a single batch of data succeeds, then any date range should succeed. For most jobs, standard join configurations, such as the number of partitions and executive memory, can be relied upon. However, if any customization is needed, then it only needs to be tested to work with a single batch. Then it can be similarly applied to any date range. After batching, we now come to Delta snapshots, our solution for efficient point-in-time joins. When users ingest batch data into the feature store, they are often generating a data snapshot, an update of all relevant entities' feature values at a given point in time. As an example, let's take a look at the full snapshot table on the left-hand side. Every day has an updated feature value for each user. The feature values here represent the number of orders a user has made, let's say in the last 30 days. For a user like Nicholas, who isn't ordering every day, feature values may remain the same across days, whereas Amit's feature values change. His 30-day aggregate number of orders was 21 on day 1 and 2, but he made an order on day 3, increasing the feature value to 22. We can see all the data highlighted in green is quite redundant. These feature values are not changing per day. If all of that data is explicitly stored and joined, it creates a huge amount of inefficiency. What we want to do instead is to only store and process data which is changing. We refer to this as Delta table, which is displayed on the right. In this format, feature tables are highly compact, storing only feature value updates for the relevant entities. Next slide. Here's another visualization that is easy to grasp how the data size changes before and after the Delta optimization. Before the change, we have a full snapshot each and every day, whereas with Delta tables, only the first day contains all relevant entities, while following days contain only updates, which are a fraction of the size. After these changes, we saw more than 10x reduction in Spark shuffle cost and join times. The larger the date range for this join during training, the larger the benefit we saw. Next. To wrap up offline scalability, let's discuss a few more optimizations we've made for joins, first being general Spark optimizations. One such change was to the Spark job scheduler. We noticed there were some cases where delay scheduling caused nearly the entire cluster to be unutilized. I contributed fixes to Spark to address these issues, and they should be available in the latest versions of Spark. We also took advantage of other configurations and optimizations which are already available in Spark, such as broadcast joins for small and skewed datasets, custom pushdown filters to reduce shuffle data size, and finally the standard, adding more executors, partitions, and memory. Last but definitely not least, our ML ecosystem makes it easy to avoid repetitive work by reusing joins. We've made it such that jobs can easily specify which data to pre-join, such that during model iterations, joins are only performed if they have not already been completed. This is useful both for development flows where a modeler is manually running various experiments and in automated flows such as hyperparameter tuning. Well, that wraps up some of our solutions for online and offline serving. And with that, I'd like to hand it back over to Amit.
All right, thanks, Nicholas. So we are switching gears now to feature management at scale. As mentioned before, the problem in front of us is the following. How do we ensure that thousands of production pipelines are producing high quality features without having individual pipeline owners carry out their own analysis or build their own tooling? Not only will that process not scale, but also result in inconsistent standards across teams. And how do we detect problems ahead of time at feature generation time versus training time when it's much harder to debug and fix data issues? And finally, how do we bring accountability to the process? Often due to oversight or lack of sufficient ownership, we may end up with poor data quality, harming the quality of predictions. So how do we surface this to teams who are then able to easily remediate the situation? So to solve this problem, we leverage Uber's data quality platform. This platform has a few core building blocks. First, metadata. The platform uses metadata to represent data artifacts, such as pipelines and tables. The metadata contains various pieces of information, such as type of storage used, type of computation, the owner, so on and so forth. Second, the platform supports Lineage. So Lineage allows you to trace data across pipelines through intermediate tables and data transformations. It builds capabilities by analyzing the ETL transformations and using metadata to trace the flow of data across various entities. Third, the platform uses the concept of tiering that defines service level agreements or SLAs to the user. Tier 1, for instance, is used for the most mission critical data, whereas Tier 5 is the least strict. Fourth, the platform supports the ability to register tests that measure certain attributes of data. How fresh is it? How many duplicate rows exist? Each tier defines a set of defaults, and with Tier 1 defining the strictest level of tests, and Tier 5 obviously the least strict. Users can also register their own test and to measure quality. And last, all data pipelines and tables require a mandatory on-call rotation so that owners can be paged upon any data quality issue. In this particular screenshot, you can see some of the results of the tests. You can read more about the Uber's data quality platform from the company's engineering blog. So how does the feature store make use of all of this? The feature generation pipelines onboarded to the feature store also automatically get registered to the Uber data quality platform. Registration involves setting the metadata, ownership information, tiering information. Tiering information flows down from the SLA of the model. So if I have a mission critical model, it'll require all the features to be tier 1 as well. And the final step is to register the tests, the default tests associated with the tier, as well as certain custom tests that the feature store does register to ensure data prerequisites for model training are met. The platform then uses the feature store data quality results as one of the components for computing model-specific quality scores. Any degradation in data results in degradation of the score as well, which is then surfaced to the model owners as well as the organizational leaders. Thus, not only are we able to automatically and uniformly measure and report the quality of data across thousands of pipelines, but have devised a way to surface the quality to model owners and engineering leaders. We believe this is one of the key reasons for driving accountability in the process, which results in the building of performant and reliable models. Switching gears to another feature management problem. From a repository of tens, 50,000 or 100,000 features, how do we choose the features relevant to the model at hand? The main problem we want to avoid is to build features from scratch every single time. And not only will this result in very expensive feature engineering cycles, but also create operational burden for having to maintain redundant pipelines. So how does the feature store deal with this? We realized very early on that manually navigating through feature groups looking for features is hard, and decided to build support for search. As you can see from this particular screen snapshot, we allow search by various things such as the feature's business entity, the feature group name, the feature name, the primary key, so on and so forth. Having found your feature, we also let you browse through standard statistics generated by the feature store, min, max, mean. We also show the data quality results that we talked about earlier. And then there's a lineage viewer as well, where you can look at the feature store's graph of pipelines. So starting with the feature producing pipelines on the right, you can browse up to the individual sort of pipelines, upstream pipelines. So as you can see, this is one of the more complex pipelines that is producing features here in this particular screenshot. Finally, basic feature search facilities may not be enough. And since it requires significant manual analysis on part of modelers, as well as to ensure that the existing features are usable by models, especially when dealing with hundreds of potential candidates. Towards that end, we have built an advanced facility in the feature store that allows features relevant to machine models to be automatically selected. Using feature metadata in palette, we are able to identify all potential candidates that are joinable with the target labels. Then using an offline feature store API, we extract all the potential features and join them into a single table. This table is then passed to Michelangelo's feature selection engine, also known as X-ray, to select features relevant to the model at hand. X-ray uses information theoretic techniques to select relevant features, for instance, by using mutual information between the features and the target labels. For more information on this, again, I'd urge you to read up our recently published Uber engineering blog. We are in the early stage of making this widely available, but have started seeing some promising early results. Just to wrap up, where are we headed? First, we are re-architecting the feature store to deeply integrate with our Uber search engine, which is being increasingly used by our recommendation systems for the highest level of scale. Second, we are building a feature intelligence layer that is able to understand how downstream ML tasks depend on upstream data at each stage of the ML lifecycle. Third, we are making embeddings first-class citizens of the platform, which means that they should be very easy to build and serve by this feature store, just like standard features. Fourth, new real-time features exist in the Palette feature store, but they take weeks or months to get right. And our goal is to build the necessary infrastructure to cut this time down to days. So just to quickly summarize, Nicholas talked about online serving for tens of millions of QPS in real time. We talked about offline serving that is able to deal with hundreds of terabytes of data. We talked about how data quality infra is able to help maintain thousands of production pipelines. And we also talked about search infrastructure, which allows you to select at scale. Finally, if this work excites you and you want to join us build this stuff, feel free to reach out to us on LinkedIn. Michelangelo has plenty of opportunities. Thank you for listening.